Hey guys, it's Miss Meneely, and I am going to give you a quick lesson on tests about a population mean. Very similar to what we've already done with distributions of the population proportion, and it's going to relate directly back to what we did with confidence intervals about a mean, using both the t-distribution and the standard normal distribution. Okay, we are going to have a short quiz today on tests about a population proportion, but I want to go through the homework first. So if you could make sure you get that out on your desk, I'm going to go ahead through the answers to the homework first, and hopefully if you did have any other questions left over that they'll be answered during this time. And then we'll start talking about tests about a population mean. Okay, so the first problem from the homework was problem number 31, and this problem dealt with a report about the percentage of high school students who have a computer at home. I believe the report said that 80% of students have a computer at home. This kid, Jason, believes the proportion is smaller than that. At his large rural high school, he chooses a simple random sample of 60 and records whether or not there's a computer at home. All you're asked to do in this example is to check the conditions for carrying out a one-sample z-test, for the population proportion. So you do want to make sure, and I didn't do the greatest job of writing this out, but you do want to make sure that you indicate that it states in the problem that the sample is random. When you're checking your n times p and your n times 1 minus p, make sure that you're using the proportion from the null hypothesis. Remember the order it goes. If you are given the population parameter, that's what you want to use. If you're given the sample statistic, then that comes second. But if you're given both, you choose the population parameter first. That trumps everything else. We're also assuming that the null hypothesis is true. So under the assumption that the null hypothesis is going to be the proportion is 0.8, that's the proportion that we want to use when we're testing the number of successes and failures. We also have to assume that the population of students in his school is above 600. When all conditions are met, then we can proceed with the test. And in this case, we'd be doing the one sample z-test for proportions. So number 31, you're just checking the conditions. In number 37, in this problem, there is no context. It just says a test of the null hypothesis where the proportion is equal to 0.5 and the alternative where the proportion is greater than 0.5 yields a z-test statistic of 2.19. So in order to determine whether or not the result is significant, you got to remember that if you're dealing with a z statistic, that we're using the standard normal distribution with mean 0 and standard deviation of 1. So here you actually have to use your normal CDF command, and you're finding the probability. And the reason that we're finding the probability that z is greater than 2.19 is because the alternative says that we're doing an upper tail test. Okay, and since it's greater than, we want to be consistent. And so we would just do normal CDF. Our lower bound would be the 2.19. Our upper bound would be 9999. The mean would be 0. The standard deviation would be 1. And this yields your p-value. And then you can compare it to the significance level. So with an alpha level of 0.05, the result is significant. Our p-value is 1.4%. So we could reject the null hypothesis in favor of the alternative. But at the 1% level, it is not significant, so we do not reject the null hypothesis. We do not have evidence to conclude that the proportion is greater than 0.5. If our test was to switch and become a two-tailed test, then we have to double the probability. And the way I would write that on my paper is I would simply say 2 times the probability that z is greater than 2.19, and then I'd have to double the probability that I found in part A. And that, I believe, gives me 0.0285. So my answers to the question would still be the same. It's significant at the 5% level, but not at the 1% level. And if you're wondering what this looks like if you're confused about that 2 times, the alternative would be to draw a picture. And so if I draw a normal distribution here, I know if I'm using my z-test statistic, I know the middle or the mean of my distribution is 0, and 2.19 is here. And so the p-value, so this is my z, my p-value then was 0.0143. If I'm using a two-tailed test, then I also have to consider a result as extreme as 2.19, but going in the opposite direction. So my z then would be a negative 2.19. You don't have to write this part, but you do need to shade the other region. And since this region is also going to be 0.0143, the p-value is equal to 2 times 0.0143. And the only time you physically have to multiply the probability by 2 is if you're using the normal CDF command and computing the p-value that way. If you're using the test menu on your calculator, so for example, if you go into your stat and over into your test menu and choose the two sample tests, I don't even know what data I have in here, but if you choose the two-sided test this way, and compute the p-value. You do not need to double it here. The calculator has already done it. But in order to write it on your paper, you would need to do 2 times the probability that z is greater than, in this case on my calculator, 2.52. Okay. In the next problem, in number 40, this has to do with side effects. A drug manufacturer claims that less than 10% of patients who take its new drug for treatment of Alzheimer's disease will experience nausea. To test this claim, researchers conducted an experiment. They give the new drug to a random sample of 300 out of 5,000 Alzheimer's patients whose families have given informed consent for the patients to participate in the study. In all, 25 of the subjects experienced nausea. Use these data to perform a test of the drug manufacturer's claim at the 5% significance level. Okay, so we want to know if we can reduce the incidence of nausea. We're told that the null hypothesis in this case is that the proportion who experience the side effect is 10%. We want to know if the new drug will reduce that. So our alternative is going to be less than. Notice that I have defined the proportion. Make sure you state that it is the proportion. Anytime you're defining your parameter, you want to make sure that you're calling it the proportion, or what we're going to start talking about today is the mean. So be very specific that you're defining the correct variable. When you're stating your conditions, again, I didn't, since this was just homework and I was taking notes, you want to make sure that you write it out so that whoever is reading your response can interpret what it says. So the problem states that we have a simple random sample of Alzheimer's patients, that they were in an experiment. When I'm doing my n times p and my n times 1 minus p, again, I'm using the assumption that the proportion is 0.1. So those conditions are met. We're also dealing with a group of Alzheimer's patients that is more than 3,000. It's given to us in the problem. Okay, so then when I do the test on my calculator, it gives me everything I need. So I'm looking at the probability that my p-hat value, make sure that this is always referring to your sample. I have seen people write the 0.1 in this spot, and that is incorrect. We're basically assuming that the true proportion is 0.1, so what's the likelihood of seeing my sample is pretty much the question that our p-value is answering. When I standardize it, we get a z-value of negative 0.962 and then a p-value of 0.168. Since 0.168 is greater than 5%, the result is not significant. That means we cannot reject the null hypothesis. We do not have enough evidence to conclude that the proportion with side effects is less than 10%. So there's no evidence that this drug is reducing side effects. Okay. In number 45, and I believe in this case I want to talk to you about what it means to interpret the p-value. In number 45, this deals with students getting their driver's license, I believe. So it says a state's Division of Motor Vehicles claims that 60% of teens pass their driving test on the first attempt. An investigative reporter examines a simple random sample of records for 125 teens. 86 of them pass the test on their first try. Is there convincing evidence at the alpha equals 5% significance level that the claim is incorrect? So it's not giving us any indication as to whether or not we think the proportion of teens passing on the first try is more than 60% or less than 60%. So this is where we're going to be doing a two-tailed test. You really need to read the context clues to see what your alternative should be without looking at the sample first. Define your parameter, and again, we're dealing with the proportion of teens passing the test on the first try. State your conditions and the method that you're using to perform the test. All of these numbers are given to me on my calculator when I do the test. I just have to figure out how to actually write that down on my paper. Because the proportion, my p hat in my sample, is larger than the parameter, another way you can look at it is looking at your z-score. Since that value is positive, I'm going to be using a greater than symbol in this expression, not a not equal to. The not equal to tells me I have to double or write the 2 in front of my probability statement. Okay, since it's a two-tailed test, I need to put the 2 in front. But if I'm doing the test on my calculator, I do not need to double the probability. It's already been done for me. Since this value is less than 5%, the result is significant. We can reject the claim. We do have convincing evidence that the proportion of teens passing the driving test on the first try is not equal to 60%. So even though my sample result was greater than 60%, I don't get to conclude that. I can only refer back to my alternative, which said that we suspected that the percentage was not 60%. Now, you may be asked to interpret the p-value, and I hope you're listening carefully, because you will be asked to interpret the p-value, and it is something that you need to do in words. So if I ask you to interpret the p-value, I am asking you to interpret the probability. What does this number mean? What is that 4.46%? Think about how we computed it. We computed it when we assumed that the null hypothesis is true. So we assumed that the proportion of teens who pass the driving test on the first try is 60%. That would be the mean of the distribution that I used to compute this probability. So if I'm assuming that the true proportion of teens passing their driver's test on the first try is 60%, I know that every sample I take is going to be a little bit different. But what are the chances that the sample I take is as extreme as 68.8%? And so that's what my p-value is giving me. It's the probability of getting a result as extreme as the one that I got, assuming that the null hypothesis is true. And so in this case, if the null hypothesis is true, that the proportion of teens who pass the driving test is 60%, then there's only a 4.46% chance of seeing the sample result as extreme as 68.8%. And then we would conclude, since that value is so low, we can reject the null hypothesis. We can conclude that the alternative is true. So please make sure you understand how to interpret the p-value. It is the probability of achieving the sample that we got as extreme as the one that we got under the condition that the null hypothesis is true. 47, this is one where you're doing a confidence interval. And I believe it refers back to the proportion of teens passing the test on the first try. And you can see in the 95% confidence interval that we get this value, that we're 95% confident that the proportion of teens who pass the driving test on the first try is between 60.7% and 76.9%. What's nice about doing the confidence interval is it gives us a little bit more information. Remember, when we were doing the two-tailed test, we couldn't conclude whether or not the proportion was greater than or less than 60%. We were only able to conclude with the evidence that we had that the proportion was different than 60%. The confidence interval, though, gives us a lot more information. We can actually conclude from the confidence interval, since both values are greater than 60%, that the proportion of teens passing the driver's test on their first try is greater than 60%. In fact, we are 95% confident that the true proportion is somewhere between 60.7 and 76.9. So it gives us a lot more information to do a confidence interval as opposed to a two-tailed test. But you'll want to make sure that you follow the directions of the question. If it tells you to do a test, do a test. If it says to do an interval, do an interval. Okay, and then I believe we had one more problem. And this is another one where you had to do the test. Okay, so hopefully these exercises helped you with the process. I'm going to ask you to go ahead and pass up your homework. You may use the orange or pink sheet that we had that outlined the inference procedures for proportions. And I'm going to give you 30 minutes to take a quiz on on tests about a population proportion. So at this point, I would like to ask the sub to go ahead and pause this video and pass out the quiz. Again, students, the only thing you should be having on your desk besides a calculator is the orange or pink sheet that has the inference procedures for proportions. So go ahead and pause and give 30 minutes for the quiz, and when the 30 minutes is up, please resume playing the video. Okay, so hopefully you guys have all turned in your quiz by now. I'd like to go ahead and ask the sub to pass out the classwork, which is entitled 9.3 Tests About a Population Mean, and the colored paper that refers to inference procedures for means. If you could pass both of those packets out, we'll go ahead and begin filling in the notes in just a minute. The process for conducting a test about means is essentially the same as it was for proportions. We're going to follow the same procedures where we state the hypotheses, define the parameter, we check conditions, we do the math, actually find the p-value, and then we interpret the p-value and conclude our test. So I'm briefly going to just kind of go through the outline of the test. These slides correspond to your notes, but it may not be a perfect fit. I made some changes and I didn't adjust the papers. I wanted to kind of do this quickly. So you'll notice step 1 where it says to state the hypothesis. We always draw conclusions about some parameter of the population, so we have to identify the parameter. In this case, we're going to be talking about the population mean. As we start combining our inference procedures, you really want to pay attention to the problem, because now they're going to all be mixed up. You're going to have proportions mixed with means, and you really want to make sure that you're able to identify the parameter correctly. Then you want to go ahead and state your null hypothesis, and it's going to be set up the same way. It's always going to be an equation where we're looking at no effect or no change in the claim. Make sure when you're dealing with means that you also include units. I will take off points if you do not include units when you're dealing with a mean. The same would be true with your alternative hypothesis. You must include units. And you will select the alternative the same way you did with proportions. It'll tell you in the problem whether or not you suspect there's an increase or a decrease or simply a difference between the claim and the group of individuals or the population you're examining. The second step for performing the significance test is your plan. This is where you state your assumptions and then verify conditions. The assumptions when we're dealing with, or the conditions when we're dealing with a mean, are slightly different than they were with a proportion. We still have to make sure that our data comes from a random sample or randomized experiment. We also need to make sure that, especially or particularly when we are sampling without replacement, that our population is at least 10 times the size of our sample. However, our normal condition looks a little bit different. With proportions, we had to multiply n times p and n times 1 minus p and check to make sure that the expected successes and failures were more than 10. With a mean, we have to either look at the distribution of the population, and oftentimes it'll tell you the shape is normal. If it doesn't, then our sample size needs to be large. In fact, it needs to be at least 30. But you'll note that in some of the problems that you're going to see from this point on, sometimes we're given small data sets and we're not told the shape of the distribution. So from this point on, if you are given data and you are not told the shape of the population, you must plot the data. You can do a box and whisker plot, you can do a histogram. I would suggest doing a normal probability plot and checking to see if your sample looks bell-shaped and symmetric. You want to really make sure that there's no skewness and no outliers. If your data is strongly skewed or if you have outliers, it is not appropriate to continue with a normal model. Or even a t-distribution, which we'll talk about as well. The easiest thing, I spelled probability wrong. Sorry, it's hard for me to write and talk at the same time. A normal probability plot, I'm just going to show you where it is on the calculator real fast. If you have data in the calculator, if you go into your stat plot menu by hitting second y equals, turn on one of your plots. The normal probability plot is this this plot right here, that very last option, it looks like a line plot, but it represents basically if you have one variable and you have data in a list, it'll linearize the data. And if the plot that is produced is linear, it tells you that the distribution is approximately normal. If it looks curved in any way, or if you have any points that are like way far away from the rest, that would indicate that you have an outlier, or that the distribution is skewed. And so continuing with our inference procedures would not be appropriate. So there is an example today that we're going to look at that requires the use of a normal probability plot, so we'll talk about it more when we get there. Okay. In terms of our planning phase and knowing which inference method to use, we have to pay close attention to where our standard deviation is coming from. You need a standard deviation to proceed regardless, but you want to know whether or not the standard deviation is coming from the population or the sample. So if you're given the population standard deviation, you can use the Z procedures. You can use a standard normal distribution with a mean and standard deviation. The formulas are given. And you can use a Z-test. If you're given the sample standard deviation, and that would be your S sub x versus your sigma, then you must use a T-distribution. And with the T-distribution, you must report the degrees of freedom. And that's what that DF refers to. And the degrees of freedom, if you remember, are computed by taking your sample size minus 1. And the formula for degrees of freedom changes depending on the type of test we're doing. If we're dealing with a one sample test for means, our degrees of freedom are 1 less. But you'll see that when we get into 2 sample situations or when we're dealing with more than one variable, the degrees of freedom formula will change a little bit. So once you state the type of test you're doing, you want to actually do the calculations. Before I get into that, this is just a brief recap of what we learned about the T-distribution in the last chapter. This is not in your notes, so if I say something that you don't remember, you want to jot it down in the margins of your notes. So the T-distribution is used if we're not given sigma, if we're not given the population standard deviation, and we're only either given the sample standard deviation or we're given data from which we can calculate the sample standard deviation, then we want to use the T-distribution. And the T-test statistic is what we'll be using instead of Z. It's computed the same way, though. If you remember, Z is equal to X bar minus the mean over the standard deviation. And since we're dealing with X bar, it would be sigma over the square root of n. Well, if we're dealing with the T-distribution, notice that we're just shifting it a little bit. We're still doing the X bar minus the mean, but the standard deviation is a little bit different because we're computing it from the sample data, which means it's technically called the standard error. When we describe a T-distribution, we have to identify the degrees of freedom. In fact, that's the only parameter. We don't have to worry about the mean and the standard deviation. The T-distribution is based solely on the sample size. And again, the degrees of freedom is equal to n minus 1. The T-distribution in general is symmetric. It's a symmetric and bell-shaped distribution. The center is at 0, but there's a lot more variation. So the spread is going to be greater than a regular normal distribution. As the degrees of freedom increase, that's like our sample size increasing, then our T-distribution is going to get closer to normal since the standard deviation of our sample is going to approach that of the population. The one sample T procedures are exactly correct only when the population is normal. So it must be reasonable to assume that the population is approximately normal in order to justify the use of the T procedures. The T procedures are going to be strongly influenced by outliers, so always check the data first. If you are ever given data, and I want you to remember this, if there is ever data on the test and it's a free response question, you must always plot the data. Always, always, always provide a quick plot. You don't have to scale the axes or anything, but just plot the data and then just define what kind of plot you did. So if you're doing a box and whisker plot, make sure you say this is a box plot and the data that it displays. If you're going to do a normal probability plot, make sure you define it that way. And you particularly want to do that when your sample sizes are small. When your sample sizes are more than 30, it's appropriate to simply say that n is greater than 30, so normal distribution is appropriate. But I will say on the AP exam, I would not expect you to get such large data distributions because it's going to take too long to enter the values. So you'll probably be given small data sets, in which case you want to plot them. Okay, let's get back to the calculation part. And again, just like with proportions, you must report your sample statistic. In this case, it's going to be X bar. Your test statistic is either going to be Z or T, and the p-value. The only thing you do want to remember is that if you're using the t-distribution, you must also include the degrees of freedom. And in terms of the interpretation of your p-value, basically what it says is, suppose for the sake of argument that the null hypothesis is true. Determine the probability, this is the p-value, of obtaining a sample result, x bar, as extreme as the one selected. And then if the probability is low, that gives us the evidence we're looking for, and that gets to our conclusion statement. But again, this is the interpretation of the p-value. And it's very important that you're able to interpret that correctly. Okay, we've already kind of done this already. If your alternative, if you look at these graphs, if your alternative is a greater than, then you're going to want to, if you're going to sketch the graph, then you want to make sure that you sketch it like this. If it's a less than, then you're going to be shading the lower tail. If it's not equal to, then it's considered a two-tailed test. And then finally, your conclusion. Is the result significant? Can we reject the null hypothesis? And then state the decision in the context of the problem. So let's do an example. In number 1, it says, in an earlier example, a company claimed to have developed a new AAA battery that lasts longer than its original or its regular AAA batteries. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average and follow a normal distribution. A simple random sample of 15 new batteries lasted an average of 33.9 hours with a standard deviation of 9.8 hours. Do these data give convincing evidence that the new batteries last longer on average? So let's go ahead and do this test. I'm going to shrink my screen a little bit so that we can see my calculator and do this one together. So the first thing we want to do is state our hypotheses. So we're told that the batteries are supposed to last 30 hours. So we're going to say that our mean for our null is 30 hours. Make sure you include the units. Our alternative, we want to see if it lasts longer. We want to see if the new batteries last longer on average. So we're doing an upper tail test. We also need to define our parameter mu. So I'm going to say it's the mean battery life for, this is the new batteries, I believe, right? Okay, so that's the state phase. Now we're going to do the plan phase, and we have to start looking at our conditions. So we want to know if the let's see, we have an SRS of 15 new batteries. So it states in the problem, states that the sample is random. We want to check to see if our sample is large, and it's not. N is only 15, so it's kind of small, but we are told that the population is normal. Okay, we have to assume, since we're sampling without replacement, that the population is greater than or equal to 10 times n. And I think it makes sense that we're looking at more than 150 batteries in the population. Okay, so with conditions met, we can proceed with the normal distribution. Or you can say a normal distribution applies. Now we've got to decide whether or not we're going to be using the T procedures or the Z procedures. We are given the standard deviation. We're told in the problem the standard deviation is 9.8 hours. But we need to think, is this referring to the population of batteries, or is this referring to the sample that we took? And in this case, since it's referring to the sample, we must use the T procedures. So I'm going to say use one sample t-test for means, and I'm going to say since sigma is unknown, just to reinforce that. Okay, now I'm going to go to my calculator. All right, I go to my test menu. This time, notice I'm going to either choose a z-test or a t-test, option 1 or 2, because I'm dealing with means. So when you're dealing with means, you're not going to see the word mean. You just won't see the word proportion. So you just got to know that it's got to be a mean. And in this case, we've decided we're going to do a t-test. I don't have the data, so I'm going to go ahead and use the stats that are given to me in the problem. The null hypothesis is 30 hours. X bar, we're told, is 33.9. The standard deviation I'm given is 9.8. N is only 15. And my alternative is the greater than. And I know some people are getting a little confused with the way it's worded because it has the greater than and then the mu sub 0. If you notice up at the top of your screen, it defines mu sub 0 is 30. So our alternative hypothesis, this is basically saying is greater than 30, which is what we want it to be. So you don't have to flip the inequality if you were getting confused about that. I'm going to go ahead and jump to calculate, and it's going to give me everything I need except for the degrees of freedom. So you will need to remember to include the degrees of freedom if you're doing a t-test. So I'm going to go ahead and say the probability that x bar, I'm going to do greater than, because that was my alternative, is greater than 33.9. When I standardize this, it becomes a t. And so t is greater than 1.54, or 1.541. And then my p-value is going to be 0.073. And I do just want to indicate underneath t that my degrees of freedom in this case, since I had a sample of 15, is going to be 14. Once I have my probability, I want to go ahead and state my conclusions. And I'm not sure if we're given a confidence level or a significance level here. It doesn't look like it. So in this case, if I were to interpret this value, if I were to interpret the p-value, I would say if it's true that the mean length of these batteries is 30 hours, then the likelihood of me seeing a sample that yielded a mean greater than 33.9, the probability is 7.3%. Since that value is not unusual, or since 0.073 is greater than 0.05, I would say the result is not significant. Therefore, we cannot reject the null hypothesis. It means we do not have convincing evidence that the mean battery life for the new batteries is more than 30 hours. You could even say we don't have evidence that the mean life for the new batteries is more than the mean life for the regular batteries. Okay, and that's how you would complete the test. So we have all four parts to the test stated. There are two more practice problems. I'm not sure how much time is left in the period, but I would like you to work together and get as much done as you can. I do want to reiterate in the next example that you are given data. You are not told in the problem whether or not the population is normal, so you must plot the data here. You must construct a plot. In number 2, you're also asked to construct a 95% confidence interval. And then this goes back to what we did in Chapter 8. And then in Part B, I believe you're doing the test of significance. Or in Part C. No, I totally lied. You are just doing a confidence interval and then using the confidence interval to determine whether or not there's evidence against a claim about, I guess, that the battery lasts at least 300 minutes. And then number 3 is another test if you get to that. And this also includes data, so you're going to want to make sure that you plot the data here as well. So I do just want to reiterate, when you have small data sets and you are not told about the distribution, you must plot the data. Now in this case, it does tell you that the population is normal. So you just want to make sure that you state that instead of plotting it. But in some cases, when you're not given the population shape, you do want to plot the data if it's given. Okay, so hopefully that is helpful to you. If you have not watched the video, Alpha, Beta, and Power, that is posted to Blackboard, please do that. It's going to be really important for our next lesson, and you'll be really confused if you don't watch the video. When you are finished with the classwork, or as it gets close to the end of the period, if the substitute could pass out the homework, that'll be due next class as well. All right, have a great night, guys, and I will be back tomorrow if you have questions or need to come in for Bulldog Block.